This is the thrust time curve from SRM. It's a typical profile with a neutral burn, and this is a drawing of the actual motor design. It features an aluminum casing of 1.8 millimeter wall thickness, an aluminum bulkhead, and an aluminum graphite nozzle. And you can see it has 6 segments of propellant. This is a drawing of the nozzle. It has an aluminum outside shell, and it has a graphite insert, which is capable of withstanding the high heat that the nozzle will experience. This is a photograph of the actual nozzle that I machined. It has 2 O-rings for sealing, and it has 8 fasteners that attach it to the motor casing. As I mentioned, it uses potassium nitrate sorbitol, potassium nitrate or saltpeter. And so the first thing to do in preparation is, of course, to weigh out the ingredients. So I'm going to show you a couple of videos. One that shows how the potassium nitrate is milled. So what I do here is the potassium nitrate comes as little frills or little pellets, and I load it into a heavy-duty coffee grinder, and it's ground up to a fine powder. Typically, I would grind it for about 15-20 seconds. The purpose of grinding it to a fine powder is to get good combustion efficiency and to get a higher burn rate. Now that's not smoke that's coming out, that's just very fine dust, so don't be alarmed. So altogether for each segment, there's 650 grams that has to be ground up. Okay, getting back to the presentation. Now I'll show you a video of the tumbler device that I made. Okay, this is a tumbler. Oh, sorry. This is a tumbler that the propellant is loaded into as a dry powder and thoroughly mixed. So this particular tumbler I made from 3D printed plastic, and it rotates at a speed of around 60 rotations per minute. And it does a very effective job of mixing the 2 powders, the potassium nitrate and the sorbitol. So I would typically mix it for about half an hour. Okay, this is a diagram of the casting arrangement that I use. It consists of a mold tube with a casting tube and spacer inside. At each end, I have a bottom cap and I have a top cap. And in the center, I have a cylindrical rod that forms the core of the propellant grain. At the top, I have a spring assembly. The spring assembly it presses against the top cap, and what it does is, as you can see in this photograph, I load it into a C-clamp, compress the spring, and this allows the propellant to cure under pressure. The reason for this is for 2 reasons. One is to eliminate all air, and secondly, to get a good bond between the propellant and the casting tube. I'll show you a video now of how I actually make the casting tubes. So the casting tubes are made out of it's a heavy paper. It's actually poster board that's impregnated with epoxy to give it a greater heat resistance. So what I'm doing here is I'm spreading glue on the surface of the paper, and then I roll it around the mandrel being the same diameter as the propellant grain. This is basically the same method I've used for all of my rocket motors. It's a method that's of making casting tube it's inexpensive. It's relatively simple to do, and it makes a good heat resistant casting tube. Okay, as you can tell, the video is speeded up. It's actually running at about 1.5 times the normal speed. So I'm usually pretty fast, but not quite this fast when I do this. So what I'm doing right now is I'm adding another piece to it to make it a total of 3 layers. That gives a total thickness of 1 millimeter. This is something of an art that takes a lot of practice to get it just right, but I've had a lot of experience doing this. Okay, what I do now is the casting tube is complete, and I use a tool to firmly press down to make sure that all the layers bond together properly. The next step is to put a temporary spacer around it. The spacer is made out of the same material, and the spacer is just to allow the casting tube to have a nice snug fit within the mold. Okay, that's the completed casting tube with the spacer wrapped around it. And what I do is I insert it into the mold. The mold is basically just a piece of aluminum tube, same material as the rocket motor casing. And there we go. That's the finished casting tube, all ready for casting propellant. Okay, now I'm going to show you a video of the actual casting process. So the casting process is basically melting the propellant. So I have a thermostatically controlled heating vessel, and I add the powder, potassium nitrate sorbitol powder, and heat it up a little bit at a time until it melts. Now for each grain segment I do individually, it requires 1 kilogram. So after about 10 minutes, you could see here it is fully melted. And now it's just a matter of heating it until it reaches the target temperature of 130 or 135 degrees Celsius. I use an infrared thermometer to check the temperature. Okay, it requires a little bit more heating. Constant stirring helps it to heat evenly and thoroughly. Okay, it's just about at the target temperature, 130 degrees Celsius. Okay, so what I do is now I pour this into the mold, or actually scoop it into the casting mold. As you can see, the slurry is quite thick, quite viscous. So what I do is I tap it to settle the propellant and to eliminate air, trapped air. And I should point out that the mold is sitting on a digital scale. So this way I know exactly how much propellant I've added, and I need to add exactly 1,000 grams. Okay, just a little bit more, top it up. So it's exactly 1,000 grams. Now that it's all been loaded into the mold, I just take the top cap, press it in place, and now it's all ready to be put into the clamp and cured under pressure for approximately 35 to 40 hours. And this is the final product. So once the grains are cast, this is what they look like. This particular propellant, KNSB, is kind of hard to ignite. So on the right-hand side, you can see that the grains are coated with a primer, and the primer is potassium nitrate charcoal, and this helps facilitate ignition. Now, before I fire the large motor, I decided it's probably a wise idea to test a smaller version. So I made this motor that I call the Muon Short, and instead of holding 6 grains, this one holds only 2 grains. But in all respects, the design is identical. It's only shorter. So I static fired this motor in February of this year. And I'll show you a video of the static firing. So thankfully that went well. I measured both chamber pressure and I measured thrust. And on the left here, the gray line is the design curve and the red line is the measured pressure. And on this side, the blue line is the measured thrust. Overall, the performance was as expected. The pressure was a little bit lower than design. largely due to the cold temperature at the time. It was 0 degrees Celsius, and the propellant burns slower when it's cold. There was also a slower pressure rise than theoretical, which is quite normal with the KNSB propellant. So overall, I was happy with the results, and it allowed me to move on and finish the full-size motor. So this motor was tested fairly recently, back on March 23rd. And I'll show you a couple of videos. One is of the setup and the firing attempt. There's the setup. There's the laptop there. There's the ignition box. Okay, now I'll show you what happened when we fired it. I'd call the motor the Super. It's kind of a nickname. Yeah, there's my baby. Weighs around 9 kilograms or 20 pounds, fully loaded. I'm going to count up to 5. Okay. 5, 4, 3, 2, 1, 0. Boom! So. Five, 4, 3, 2, 1, 0. Yippee, it worked. I was mighty relieved and happy. The only drawback or the only downside to the test was that I did not successfully collect any data. The laptop computer that I was using literally froze up. It was minus 9 degrees Celsius at the time. And when I looked at the laptop after the test firing, it was frozen. So I plan to refire this motor later on this year before it starts to get too cold again. But based on the video and based on the burn time, it seems like it was a nominal burn. So that completes the part 1. And now I'm going to talk about development of epoxy-based ammonium perchlorate propellant. The goal is to develop a simple, safe, and good performing ammonium perchlorate composite propellant using common epoxy as a binder. A lot of rocketry enthusiasts use HTPB, hydroxy-terminated polybutadiene, as a binder. It's obviously a good binder. It's energetic, but it can be tricky to use. It's very complicated, uses some nasty chemicals. For example, this recipe here, you can see it has the ammonium perchlorate, aluminum powder, burn rate suppressant, HTPB, plasticizer, cross-linking agent, anti-foam agent, curative, slow-acting curative, cure catalyst. So it can be kind of complicated to make it, and quite process sensitive, that that could lead to mistakes and errors in formulating the propellant. So I decided I wanted to keep my formulation very simple. So I had some West system epoxy on hand. This is a pretty common 5-to-1 ratio epoxy system, 5-part resin to 1-part hardener. So the first formulation I tried was with AP epoxy and red iron oxide as a burn rate accelerator. So I test fired this motor in a small nozzleless motor with a very low KN. Not knowing what the burn rate was like, I decided to be kind of conservative. Well, the result was not too encouraging. A loud bang as the rocket cathode. So I kind of put this project aside for a little while. Although a few years later, I decided to give epoxy a second chance. So why did the first attempt fail? Well, looking back in my notes, I saw that the density ratio of the propellant that I made was 0.83. In other words, the ratio of the actual mass density to the theoretical was only 83%, which means that the propellant is very porous or full of air. And you really should have a density ratio of at least 95% with the minimum amount of porosity. So obviously there was some kind of reaction between the West system epoxy and the AP. So I thought, well, why not try a different epoxy system? And in addition to that, I would vacuum process it after mixing and cure it under pressure as I do with the sugar propellants. So I happen to have on hand this epoxy, New Luster 55. It's 2 equal parts hardener and resin. So I thought I'd give that a try. I made a mixture with epoxy, AP, and iron powder as a thermic agent, and I was pleasantly surprised when my density ratio was greater than 95.95, showing that the propellant was had very little porosity. So I test fired it, and I'll show a little video of the test firing of this motor. Zero. All right, it worked. That showed that it was possible to use epoxy as a binder. The process that I use to prepare it, I'll just show you quickly. Basically, it's a matter of blending the AP and lampblack, which is an opacifier, with the epoxy, and then mixing it to a putty-like consistency, vacuum processing to remove any gases, and then rolling it into little balls that are packed into the mold. And then it's cured under pressure, similar to my sugar propellants. You can see it. I have a spring in here which regulates the amount of pressure that it cures under. So this is a photo of some typical propellants that I've prepared. Density ratio is typically greater than 0.98. And over the next while, I managed to develop quite a few different formulations using epoxy. I've used 3 different binder systems. I've used the New Luster epoxy. I've used a similar one called New Classic. And I've even was successful in using West system. The key was to vacuum treat it and to cure it under pressure. I also have incorporated certain additives like aluminum or iron powder. And I've used the ones that are highlighted in yellow for launches of several of my rockets, and it has proven to be very reliable and powerful propellant. I'll show a video of a typical firing of a motor. using this propellant. Okay. I'll give count up from 3. 3, 2, 1, 0. Okay, I'll close out this section just to talk about friction sensitivity testing that I did on this epoxy-based propellant. This propellant is a little bit hard, unlike HTPB-based, which is rubbery. So some concern might arise: is this friction sensitive? Is there any chance of it, catching fire when you're drilling it or cutting it or whatever? So I designed and built a friction testing apparatus. And the way this works is I have a test specimen of propellant. It's mounted on the bottom of this anvil. And there's a downward force applied to the anvil using this lever arm with a weight hung on it. By choosing what weight you use, you could vary the amount of force or pressure acting on this test specimen. To generate friction, I have this steel blade that's pulled fairly rapidly. So you have a combination of force or pressure and frictional energy being added. These are some of the test specimens that I prepared for this type of testing. I'll just show you a video of a test that I did. So this is a video of initial trials that I did just to test out the apparatus to make sure it works as I expected. Yeah, when there's a reaction when you could hear a sound or smoke or smell or flash. Now I'll just point out that to test the apparatus, I made a special test specimen that's known to be friction sensitive. It's made from potassium chlorate, epoxy, sulfur, milled glass, and charcoal. So this is, again, just to test the apparatus to see how it works. Zero, and that's when I'll pull it. 0. 3, 2, 1, 0. Yeah. 3, 2, 1, 0. Okay, so you can see that the apparatus definitely does work. The friction sensitive specimen did show a positive reaction. You could hear the crack sound, you could see the smoke, and you could even see flashes. Then I tested all the propellant specimens, and the good news was there was no positive reactions, even though I used a contact pressure as high as 8 megapascals. The propellant tended to shear or shred rather than generate frictional heating. So this picture shows an example of a tested specimen. And that's the end of my presentation. Okay, I'll stop presenting.
Thank you very much. We are waiting if someone has any question. In that case, let me see. Thank you very much for your presentation. Really interesting, to be honest.
Okay, so you saw everything. I heard everything. Okay.
Yeah, I think. Let me see. It was a Does all your experiments are uploaded on your web page?
Okay. Not yet. Not yet. They will be eventually.
Oh, okay, thank you. With which equipment have you determined the velocity of combustion of your experiment? How?
Sorry, could you repeat that? I didn't quite.
Yes. With which equipment of, I don't know, medition maybe, have you determined the velocity of combustion of every single experiment?
The combustion?
With how do you measure the velocity?
Oh, of the propellant or of the well, I measure the thrust and I measure the chamber pressure of the motors using like a load cell that measures the force, and I use the pressure sensor to measure the chamber pressure. And from that, I'm able to calculate the performance of the propellant, the specific impulse and the other characteristics like burn rate and that sort of thing. Does that answer the question?
And for obtaining the curve of the thrust, and the time, it has to be like calibrated or certificate in some way. Like how's the standard? How do you standardize the to measure
How
the
do
curve?
I? Sorry, I didn't quite understand because your voice is breaking up a little bit.
Sorry. And for obtaining the curve of the thrust, for example,
Yes.
it has to be calibrated or certificate to obtain
Yes.
which one?
That's great. Yeah, I calibrate it. I have I basically use just I have an apparatus that I've built that I apply weights onto the load cell, and from that I do the calibration.
Oh, okay, thank you very much.
Okay.
And well, how do you calculate the velocity of the burden? Is the same way with the curve?
The velocity of the burn?
Yes.
Well, I show on my website, I show a couple of methods how I do that. One is I use like a strand burner, it's called, where I burn the propellant under pressure and then measure the rate at which it burns. But I also, it's possible to determine the burn rate from static testing by measuring pressure. And by knowing the pressure and knowing the burn area, how it changes as a function of time, it's possible to calculate the burn rate of the propellant. At least that's the way that I've done it.
And another question is, what is the specification of the first motor for which mission or altitude?
Altitude, the way with the charge way. I guess.
Sorry, the altitude?
We studied what are the the characteristics of the first motor, which mission is altitude, weight.
How much does it? How much the weight in the propellant in that case?
Yeah, I'm sorry. It's kind of hard to hear because you're breaking up. So it was kind of hard to hear your question. I'm sorry.
We're going to
Write it.
wait, yeah.
Yeah.
Hi, Mr. Nakka.
Oh, hello.
Hi. So we are here, and we want to show you some of the projects
Okay.
of the teams that we have here at the conference.
Okay.
So let's see. For example, we have.
Okay. Wow.
Oh, let me see. Let me clear the filter. Sí, quiero quitar el filtro. Just give me a second to remove the filter.
Okay. Okay.
Sí, sí, sí.
I don't hear anything now. Okay. Okay, so I got your question. Can you hear me?
Yes, yes.
Yeah,
we can hear you.
Okay, okay, so I got your question.
One of the rockets.
So you're interested in the M motor that I was talking about.
Hello.
Hello. Hello.
I love your MVP compilation.
Thank you. Thank you.
Hello, Richard.
This is a rocket.
Oh, wow. That's a nice one. Very nice. Thumbs up.
This is another one of the team's rockets. They're called Ignitia.
Oh, nice. Very nice.
Here we have some of the other developments. This is another team right here. This is also the rocket.
Wow.
Hi.
Hello.
Hi. Hello.
That's a lot of very nice looking rockets there. Very nice looking.
This is another team. They're working on 3D printing some parts of their systems. Oh, and this is the rocket. They have some cool design here. As you can see.
Oh, cool. Yeah, very cool. Nice.
And
When
I believe they base their design based on your equations, actually.
Oh, okay,
Equations-
I'm flattered.
Usaron ecuaciones de Nakka para desarrollar el. Sí, they use your equations to design the
Right.
part of the motor. This
Oh,
one
very
right-
nice. A nice looking nozzle.
They're going to incorporate. They're working on integration right now.
Nice.
Also, we have other teams. This is the rocket. Si quieren saludar a Richard Nakka, aquí está. Some other team is working on the computer integration systems. And this is basically the teams. They have some information on their tables, up their own workstations.
Right. Very nice.
And
I'm very
this is
very impressed. Yep. Very impressed. That's a lot of effort being put into it. Yep.
Yeah,
When
yeah.
when do you plan to do a launch event?
So launch window is tomorrow.
Oh,
Starts
really?
tomorrow at 8 a.m.
Oh, wow. Wow.
and it ends at around 3 o'clock.
3 o'clock. Okay. Wow. I'll be interested in hearing what happens.
This is another team. Si quieres saludar, Richard.
Hello.
This is also their workstation,
Hello.
their project.
Take pitch.
They have their shirts.
Oh, yes. Cool. Cool.
This is another workstation of another team.
You have a lot of teams there.
Hello, Mr. Nakka.
Hello.
Morning.
Hello. Nice to meet you.
This is another team. They have their rocket here.
Hello. Nice to meet you.
Workstation. Another team. Some other teams are in the save review right now.
Okay.
Safety review. So some tables are empty, but yeah, I just wanted to show you a bit of the work and
Yeah, I'm very
the
impressed.
of the teams.
Very impressed.
They follow
Congratulations.
you. They love your work. They base a lot of their development actually on your work. So thank you for building that for us.
Well, thank you for using the information to come up with such an amazing event, and I wish you good luck with it. And I look forward to hearing about how your rocket launches go.
Thank you very much.
Yeah. Keep in touch. Yep. Okay.
We have another question here. Sí, dime.
Que se puede venir un año.
Oh, they're asking like they would like to see you here next year
Oh,
in person.
well, maybe that'd be very nice. I'd love to.
Yeah, you can come down to Mexico.
Yeah.
And see the launches and the teams, meet them.
Yeah, that'd be fantastic. Yeah.
Yeah, for sure. That would be great. And another team. Larry came from the
Hello.
you.
Very nice.
Yeah, so thank you very much,
Okay.
Mr. Rich, for attending this invitation, and hopefully we can have you here
Okay.
further events.
Is that Philippe I'm talking to? Who am I talking to, by the way?
I'm sorry, I wasn't able to hear you very well. Can you repeat that?
Oh, is this Philippe I'm talking to?
Yes.
Yes. Okay. Nice to meet you. Okay, I have to go. So again, I wish you good luck, and let me know what happens with your event. And I'm very impressed and honored to be part of it.
Thank you.
No,
very
thank
much
you.
for
Thank you for you.
Okay, thank you. Bye-bye.
Bye.
Bye-bye.
Bye.
Bye-bye.
Sí, hemos hecho. Nos hemos basado mucho en